Testing on YouTube. Testing. Testing on YouTube. Alright, audio quality seems good on YouTube. Just got one more to test. Audio quality seems good on YouTube. Test on X. Let's go here. Scheduled. All right. Petit boo. She's here. Got anything to say to the stream? Huh? Say hi. Yeah. Okay. How's it going, Josh? Our house has been waiting for you to cover this since it dropped. What do you mean by house? Are you part of some kind of like commune or just like a family or? Some espresso here. How's it going, Ed? All right. As soon as it hits 8, we're going to start. Call it a nerd collective. All right. I like that. Kind of like a hacker house, it's sounding like. How's it going, John? I'm waiting for the 8 a.m. to start so I can blow this horn. We got the spiral didgeridoo today. Going back to the original. Gather round, kids. It's time for another Hoopo stream. I don't know, I hope not. I feel like I swear too much for children. But, alright, I think we're ready to go. Alright. Welcome to another Hoopo stream. Today we're going to be reviewing a paper called RTX. So this is a paper by a whole lot of people. That might literally be the most amount of people I've ever seen on a paper. It takes up pretty much the entire page. And the official name for the paper is Open X Embodiment, Robotic Learning Datasets, and RTX Models. So RTX here refers to robotic transformer, and then X. There was earlier papers. There was RT1 and then RT2. I think we did streams on both of those papers. And then the embodiment here refers to the fact that this is going to be an embodied AI, right? A lot of people are making a kind of a distinction between AIs that are constrained to just a computer, like your ChatGPTs, and then AIs that are embodied, as in they actually have a body or they're a robot. And then the open here refers to the fact that this is open source, or at least it is more open than most AI initiatives. But basically what this paper is, it's a large data set and then a transformer model that has been trained on that data set. But it's a very large data set of over 1 million episodes, and you can think of an episode as basically one maybe like 15-second little action that a robot does. So we're going to see that a lot of this paper is robotic manipulators. So basically arms with little hands, and hand is actually maybe too much of a fancy word. It's really just what are called parallel jaw grippers, or different variants of, like, basically it's like a little pincher, right? So you got 1 million of these little 10-second little pinch grasps with 22 different embodiments. I've never really heard this terminology before. This is starting to be new. I would just call this 22 different types of robots, but now I guess they're kind of leaning into this whole embodied AI. So an embodiment is a particular type of robot from 34 different research labs across 21 different academic and industry institutions and 311 different environments. So pretty big, pretty massive monster data set. And yeah, I think I'm excited to see what they have to say about it. Question from Adam Levy. I want my kids to understand how redundant they will likely become when they grow up. Yeah, I don't know if redundant is the right word. I think carefree is more the better word. I think it won't matter. I think you'll basically be just playing video games. I missed the tribe, Colin. Oh, no. All right, so very big author list and very tiny abstract. This is potentially the smallest. Oh, okay, I guess not. I guess it continues over here. Never mind. All right. So large high-capacity models trained on diverse data sets. So high-capacity, sometimes you hear the word model capacity, and that generally refers to the size of the model. So high-capacity model is a big model. A small-capacity model is a small model. So large high-capacity model seems a little bit redundant there. Trained on diverse data sets have shown remarkable success on efficiently tackling downstream applications. In domains from NLP, NLP stands for natural language processing. That's like the OG word that people use to refer to anything that deals with language and text. I feel like NLP as a term is kind of becoming less and less common. To computer vision, this has led to the consolidation of pre-trained models with general pre-trained backbones. So backbone refers to kind of the block of your model that usually consumes the input in its most raw form, and then from on top of the backbone there'll be like a head. And sometimes the word backbone is used in reference that you'll pre-train an entire model in some kind of self-supervised way, and then you'll keep the backbone, but then you'll replace the head and put a classification head or some other type of specific narrow domain. But all of this terminology is starting to become more fuzzy as kind of the whole AI world changes and all the different ways that we did things are done differently. So what does pre-training even mean nowadays as well, right? Serving as a starting point, can such a consolidation happen in robotics? Conventionally, robotic learning methods train a separate model for every application. This has been true, at least when I was doing robotics. You basically trained from scratch every time. Maybe not the actual vision backbone. Maybe you reused a vision backbone that was pre-trained on something like ImageNet, but the model itself was largely trained from scratch for that very specific robot and that very specific application. Every robot and every environment, can we instead train a generalist robot policy that can be adapted efficiently to new robots, tasks, and environments? In this paper, we provide datasets in standardized data formats. Okay, so if you're going to train a generalist model, you have to figure out a way to map all the data into the same format, right? That seems like the kind of hardest thing to do for robotics because there's just such a varied amount of robots, different numbers of joints, different control speeds. There's so many different ways that make it different, right? It's not like text data where every single medical journal and every single chemistry journal, right? All of those can just be turned into tokens and you can just train on both of them equally, right? So text has kind of this inherent kind of unifier because it is the standard data format. Make it possible to explore this possibility in the context of robotic manipulation along experimental results that provide an example of X robot policies. We assemble a data set from 22 different robots collected through a collaboration between 21 institutions demonstrating 527 skills. It's kind of weird. Oh, never mind. Okay, those numbers match. 21 institutions, 22 different robots, 22 different robots. We show that a high-capacity model trained on this data, which we call RTX, the robotic transformer, exhibits positive transfer and improves the capabilities of multiple robots by leveraging experience from other platforms. So what does positive transfer mean here? they're referring to what is called transfer learning. So transfer learning is when you train on one task and then you try to transfer that performance or intelligence onto a different task. So if you have negative transfer, that means that learning on the first thing makes you worse at the second thing, right? Positive transfer means that learning on the first thing makes you better at the second thing. And there are plenty of examples of negative transfer, right? I think one example that I remember is badminton and tennis. Like the way that you swing in badminton is different than the way that you swing in tennis. And sometimes if you spend too much time playing badminton, you're going to actually, it's more difficult to unlearn what you learned in order to play tennis. I don't know. Maybe that's a terrible analogy, but all right, we got basically a big ass data set and we're going to do some training on it. Introduction. This is actually not a very long paper, so we'll see exactly what they do. Yeah, look at this. It just kind of cuts off after like 4 pages, so it's not a lot to it. Central lesson is that large-scale learning from broad and diverse data sets. Everybody loves that, right? The bigger the variance in your data set, the larger your data set, the better. And sometimes the size of the data set is kind of a proxy for the diversity of the data set. And almost maybe what matters more is the diversity, and it just so happens that diversity tends to come with scale. So if you have a big data set, it tends to have more diverse stuff in it. So sometimes when people say more data is all you need, really what they're trying to say is that I need more variance in my data. I need my data to cover a larger percentage of the total actual real space. Large-scale general-purpose models, typically trained on large, can often outperform their narrowly targeted counterparts. Yep, this is kind of the story of AI in the kind of past 5 years where people realize that, hey, actually just train a very generic algorithm on a huge data set, and that's going to do better than training a very specific algorithm that's targeted on a very specific type of task on data that's filtered and cleaned for that very specific tasks. And I still feel like people haven't learned this lesson. You know, sometimes people call this the Rich Sutton bitter lesson, but like even today, right, there's all these people who are like, oh, okay, well, we're going to take the large language models and we're going to fine-tune them, and then we're going to have all these different little fine-tuned language models for each narrow task. And you kind of just have to look at them and be like, that's the same kind of thinking that we used to have, and we learned that that kind of thinking is wrong. You're thinking in the wrong direction. You're trying to take the more general thing and narrow it down. That's not the right way. Take the more general thing and make it even more general, right? That's the direction you should be thinking in. How do I increase the scale? How do I increase the data set rather than how do I take this thing and make it more narrow? Open vocabulary image classifiers, so everybody's favorite CLIP. Trained on large data sets scraped from the web tend to outperform fixed vocabulary models trained on more limited data sets. LLMs trained on massive text corpora tend to outperform systems that are only trained on narrow task-specific data sets. The most effective way to tackle a narrow task is to adapt a general-purpose model. However, these lessons are difficult to apply in robotics. Any single robotic domain might be too narrow, and while computer vision and NLP can leverage large data sets, comparably large and broad data sets for robotic interaction are hard to come by. Yeah, and it's also the format is just difficult, right? Because there's just a lot of different types of robots. So getting that correct is hard. But maybe some of the stuff we've seen is that we're starting to see the beginning of being able to take a language model and then just zero shot it to something that it's never seen before. We saw this in the Transformers are General Pattern Machines paper, that maybe we don't need to even have this idea that they're doing in this paper of like fine-tuning a language model on a robotics data set. Maybe you just zero shot the next generation of language models directly to the robots, and you don't need any of this custom specific robot data. Okay, so they're talking about data sets here. These data sets are often still narrow, either focusing on a single environment, single set of objects, or a narrow range of tasks. How can we overcome these challenges and move the field towards a kind of large data regime that has been so successful in other domains? Inspired by this generalization, we take the perspective that the goal of training generalizable robot policies requires X embodiment training with data from multiple robotic platforms. While each individual robotic learning dataset might be too narrow, the union of all such datasets provides a better coverage of variations in environments in all robots. Agreed. Generalizable robot policies requires developing methods that can utilize embodiment data. Even if such data sets in their current size are insufficient to attain the impressive generalization results, in the future, the union of such data can potentially provide this kind of coverage. We believe that enabling research into X embodiment robotic learning is critical at the present juncture. Okay. Kind of like a nothing burger a little bit. Like, they're just kind of like saying the same thing over and over again in like 10 different ways. But more data is good. More diverse data is good. And if you want to make robotics better, let's just get more data. All right, so how are they going to do this? 2 primary goals. 1, demonstrate that policies trained on data from many different robots and environments enjoy the benefits of positive transfer. Okay. And then 2, provide data. Okay, our work focuses on robotic manipulation. That's another thing I noticed here. So this kind of work, they have a bunch of different releases. So obviously they have this paper, they have this blog post, which is basically just the paper but summarized. But they also released like links. If you click on the code, it leads you to this Google Cloud storage bucket. It's kind of like a S3 bucket, I guess. And in here they have some stuff. And they have this 738 megabyte RT1X. So this is a saved TensorFlow model. You can see here from the specific training step. So this was trained probably for more, and then they picked this specific checkpoint here. Checkpoint 2,272,480. So that's the iteration that they chose. It's a little bit less than 1 gig, so not a massive model. This is just a very small model. Not very small, but small. And then they also released these 2 Python notebooks, which we're going to look at for sure. We're going to see those. But what I wanted to show you guys is this. This is another thing they released. This is a Google Sheet that has basically all the different robots that were used for this data set. And you can see here, for example, let's try to zoom in here. Can I zoom in? 200%. Here we go. Can I just like move this table here? All right, but anyways, here you have the robot. You have Google Robot. So the Google Robot is, we've shown it before, but it's basically a mobile manipulator. It looks like a little, this is it. This is the Google Robot. It's basically an arm on top of like a little Roomba, and then it has this little laser scanner there, and it has a bunch of cameras on inside a head, and you can control the Google Robot via VR. So if you actually come here, they say it's a Google Robot. It uses just a normal little gripper, right? That little like pinchy gripper. They have a ton of this. It's a mobile manipulator, so it's an arm on top of a mobile base. And then what am I looking for here? Boom. The data collection method is human VR. So you can see there's different ways to collect data on these different robots, right? The way that you control these robots is different. So VR is kind of like the gold standard because you can basically move, you see what the robot is seeing. So you can sit there and basically pretend to be the robot and then collect a bunch of experience. So they have some humans sitting here controlling this robot in VR, grabbing, and obviously it's not the researchers themselves collecting 73,000 episodes of that. It's probably some kind of lower wage kind of contractor person who's doing that, but it's a whole lot of data to collect. Another common way of controlling these robots is what's called a space mouse. So a space mouse, I pulled up here for you guys as well. This is used in 3D modeling, but it's basically like this little nub, and you can rotate the nub either way, but then you can also push down on the nub and kind of tilt the nub. So it's basically a mouse that doesn't just move in 2D, right? Like the mouse that you have right now, it just moves kind of in this flat plane, but this mouse can also kind of like tilt and rotate. So they're quite popular for robotics because you can kind of move the arm with them, right? So that's another one that comes up here. But you have other things here such as joysticks, scripted, which means someone made like a little script that moves the robot at specific points. Expert policy, that's some heuristic that someone came up with. But yeah, these are all the different arms. And that's another thing to notice about here is that, as they said here in the paper, our focus works on robotic manipulation. Look at these robots. These are all arms. Arm, mobile manipulator, mobile manipulator, arm. Like the only ones that aren't are like the Turtlebot, which is the ROS It's like a little, basically like a little Roomba. You have whatever jackal here is, but there's no quadrupeds here. I guess maybe this one? They have one quadruped. They have 20 episodes of a quadruped. Doesn't seem like a lot, right? So it's like it's overwhelmingly dominated by these manipulator and arm robots. So something like Tesla's Optimus robot, probably not going to use this. Maybe they use this data set for the actual hand of the Optimus, but probably not for the walking. The Digit robot, probably not going to use this. So it is still constrained to arms and manipulators, which is the actual terminology for arms. Cool. Let's get back to the paper. Question from Neutral. Have you done any recent sessions on GNNs? I have not. GNNs are graph neural networks. IMO, like I've never really been into graph neural networks, but I feel like architectures that are specialized to specific things, such as graph, right? A graph neural network is specialized to graphs. I don't know if that's going to be the way. I think much like we read here in this first paragraph, task-specific architectures, data-specific architectures are going to kind of disappear into the fog of history, right? Eventually, like, everything can be turned into text, and if everything can be turned into text, then the giant model that's trained on all the data is going to be basically a text-based model. So if you're working with a graph, what you're going to do is going to turn that graph into text and then use a giant pre-trained language model to do whatever you want to do with that graph. So I don't know. I'm generally not bullish on architecture that are specific and narrow to one kind of type of data or one specific task. And I kind of bucket graph neural networks into that. Sorry if that's not the answer you wanted to hear, Neutral. Okay. So they train RT1 and RT2 on 9 different robotic manipulators. We show that the resulting models, which we call RTX, can improve over policies trained only on data from the evaluation domain, exhibiting better generalization and new capabilities. We provide the OpenX embodiment repository, which includes a dataset with 22 different embodiments from 21 different institutions that can enable the robotics community to pursue further research. Our aim is not to innovate in terms of the particular architectures and algorithms, but rather to provide the model that we train together with data and tools to energize research around X embodiment robotic learning. Sick. All right, related work. Let's see. This is probably just going to be a bunch of references to their previous stuff, but let's see. Transfer across robotic embodiments and simulation. So transfer in robotics, a lot, kind of for the longest time, what really that's been focused on is what's this task of sim to real. So can I train something in a simulation, right, with a simulated version of my robot, and then can I transfer that into the real world? And that's not like easy and out of the box, right? There's a lot of trouble generally because there's differences in your simulation in the real world. So even just taking the same exact version of your robot in simulation and using that to gather data and then training a model specifically on that and then trying to transfer it onto a real robot has been difficult, although I feel like it gets easier and easier every year. But there is a bunch of work on that. Incorporating representation, learning policies, decoupling robot and environment representations. What else? Methods that transfer across human and robot embodiments also often employ techniques for reducing the embodiment gap. So here they're talking about the more there is a gap between one embodiment and the other embodiment, the harder it is to transfer between those, right? So if you have one robot arm that, for example, this little robot arm here only has, I don't know, maybe 4 joints. Like what is this? 1, 2, 3, 4, and then the gripper. Compare that to kind of some of these more complicated industrial arms that have like 7 joints usually, right? It's going to be harder to transfer something from that 7-joint arm to the 4-joint arm than from a 7-joint arm to another 7-joint arm. So give me 1 second. I'll be back. All right, I'm back. All right. Unlike most of these prior works, we directly chain a policy on the X embodiment data without any mechanisms to reduce the embodiment gap. And There you go. That's the Rich Sutton bitter lesson, that we spent all this time thinking about like how are we gonna do the sim to real transfer and like one embodiment to another embodiment, and turns out you don't need to spend any time thinking about that at all. Just spend all your time and effort just trying to 10x the amount of data and 10x the model size and 10x the amount of training that you do, or the training time, and you just solve all these problems for free. So I don't know, maybe we don't need to worry about these things. Robot learning community has created large open source robot learning datasets such as grasping, pushing, teleoperated, with the exception of RoboNet. When is this? RoboNet. Large scale multi-robot learning, published in 2019. Cool. So people have been trying to do this before. These datasets contain data of robots using the same type, whereas we focus on data spanning multiple embodiments. The goal of our data repository is complementary to these efforts. We process and aggregate a large number of body dataset or prior datasets into a single standardized repository, which shows how robot learning datasets can be shared. I think they're focusing maybe a little bit too much on this multiple embodiments. The embodiment is important, but also the environment. Like, it's not just the robot itself, but also the environment that it's in. And I feel like a lot of these datasets, they're just in these very narrow, constrained environments. Like, for example, this right here, right? It's like you're always on top of a table, and it's like the same exact table every time, right? The same exact height of table every time, the same exact objects every time. So, like, the variance of your data set should not just be, here's 10 different robots doing a pick and place task, but it should be beyond that as well, right? You want different lighting, different heights of tables, different tables, and things that aren't tables, right? Like picking out of a washing machine or something like that. So maybe more emphasis on the environment would have been useful there. Prior work has aimed to endow robots and other agents with the ability to understand and follow language instructions, often by learning language condition policy. So policy is what actually determines the action that you take, right? A trajectory is a series of actions. A policy is what kind of basically a neural net that actually outputs, here's the exact action that you're going to take at this exact point in the state space and exact point in time. And you can condition that little neural net that outputs the action on language, right? And that's what you're seeing here, right? You're conditioning this policy, which is controlling this arm, on this language or this text that says move apple between can and orange. And then your little policies basically coming up with the little sequence of actions, every single little micro movement at some control speed to pick that up and then move it. Still seems kind of shaky though, right? Like look at just all the unnecessary amount of shaking that it's doing. But still quite impressive. Following previous works and pre-trained vision language and robotic imitation learning, we study both forms of pre-training in our experiments, specifically following the recipes of RT1 and RT2. So these are the two previous papers. Let's look at this figure. The OpenX embodiment dataset. The dataset consists of 60 individual datasets across 22 embodiments. The Franca robot has the largest diversity in visually distinct scenes due to the large number of Franca datasets. So this is the Franca robot. It's a arm, right? So you basically, it has a hard base. You literally screw it onto the table. You could put these on a little mobile base if you wanted to and make it a mobile manipulator, but most of the time these are just basically screwed onto a table. And it has, I think, 7 total joints. Yeah, 7 degrees of freedom. What is payload of 3 kilograms, so can't be lifting huge weights with this. And it has kind of a limited little box that it can work in. Write stuff for C++. You can use ROS if you want. But yeah, these are quite popular. Because I think they're actually quite cheap as well. A lot of like industrial robots are actually quite expensive, and then a lot of them are kind of unsafe, but this one is kind of like the outside is plastic, it's nice and cushy. You know, it's probably not going to kill someone, so people love these more human-friendly or collaborative, I think is the buzzword that they use, collaborative robots. Okay, wait up, we were up here. The Franca robot, the X-arm, and the Google robot contribute the most trajectories due to a few large data sets. Okay, so the Google robot data set, which we saw has the most, right? This is something like 73,000 trajectories, and then I guess not. Look at this, 580,000 episodes from this KUKA robot. Over 700 gigs. Seems like a lot. The dataset contains great diversity of skills and common objects. Right, so common dataset objects. So I guess this is what you're normally dealing with here. You got utensils, appliances, food, furniture, lots of counters, drawers, tray, bowl, pot, cup, hexagon, triangle, heart, cube. Scenes per embodiment. Something seems wrong here, right? Why are they not talking about this one here? It seems like this one has the most data, but it's not present in the paper. It's kind of weird. Okay, but you got the Google robot, the Franca, trajectories per embodiment, the X-arm, Google robot, KUKA. Well, here it is. Okay, finally it's represented. Data sets per robot embodiment. Look at this. You still got people using the Baxter robot. This is an old robot. I think this company actually went under, the company that is Rethink Robotics, but I guess people are still using these old robots. Got KUKA. Sawyer's another Rethink Robotics robot. Picking, moving, pushing, placing, sliding, but all of these are within the context of manipulation. So moving is not, and even pushing, you're not like pushing actual things around in the real world. You're kind of like pushing objects on a table. So I think, to me, this data set is still very constrained to manipulation, but even having a generic data set for manipulation is pretty good. So all right, let's see. Large-scale data, pre-trained model checkpoints. That is, the pre-trained model checkpoint is this right here. This RT1X-TF TensorFlow trained for this many steps. For X embodiment, we provide and maintain the following open resources. The actual data set, if you want to fine-tune on that yourself, or just the checkpoint. And one thing that we kind of see more and more is that pre-trained model checkpoints are effectively the data set. So like we keep seeing this in computer vision papers, but rather than using a data set in the raw form, you can basically use that data set or the intelligence of that data set by just using the model, right? So something like CLIP or Stable Diffusion, those are in a sense just kind of a compressed form of some original data set. So you don't actually need to use the dataset that Stable Diffusion was trained on. You can kind of use the Stable Diffusion model itself as a kind of pseudo dataset, right? You can use CLIP, that model itself, as a kind of pseudo dataset. It's like basically models are just compressed datasets, and you can just use the models rather than actually using the dataset. So you could probably do something similar here, where you probably never actually need to download this robot dataset. You could, if you want to do some kind of cool new application, just use this model and figure out how to use the model rather than the data set in its raw form. So this pre-trained model checkpoint is kind of the data set if you want to think of it that way. So it's 700 megs. You could download that really easily, way easier than actually downloading the real data set, which is probably, might even be like terabytes. Yeah, we're talking like some of these are 700 gigabytes. So like for sure, if you downloaded all of this, it would just be way more unwieldy and impossible to use than just this pre-trained model. We intend to use these resources to form a foundation for X embodiment research in robot learning. That's kind of cool. Little open source foundation, I guess. Open X embodiment is a community-driven effort. We hope to further broaden participation and grow the initial X embodiment dataset. In this section, we summarize the dataset and X embodiment learning framework before discussing the specific models we use to evaluate our data and experimental result. The Open X embodiment dataset contains 1 million plus real robot trajectories. Okay. Pulled a bunch of things. We use the RLDS data format. RLDS stands for Reinforcement Learning Dataset. So it's a specific type of reinforcement learning data set. You see here episodes. Episodes are composed of steps, and then each step has some observation, action, reward, discount. So it's basically the Markov decision process as a format. And maybe this is the one thing I don't really agree with here, where like they're talking about forming a foundation and making a community-driven effort, and like, you know, we really want people to join this effort, but then you look at the way that they're doing it here, and they're using TensorFlow. This is TensorFlow data sets. That's not what the community wants, right? Like, so I like this. Papers with code. Let me do a quick diversion here, but you go papers with code, you go to trends, and you go to frameworks. So look at TensorFlow here. Nobody uses TensorFlow anymore. It used to be the case that TensorFlow was the way to do it. And actually, TensorFlow was the first thing that I learned, right? I learned TensorFlow before I learned PyTorch, before I learned JAX. But TensorFlow is dying. No one wants to use TensorFlow anymore. No one wants to use TensorFlow datasets anymore, right? So if you're trying to create an open source kind of community-driven effort, why are you doing it all in a dead framework, right? Why are you not using JAX? JAX is the new TensorFlow. JAX also comes out of Google, but it's cooler. I don't really know why JAX is more popular than TensorFlow. I think part of that reason is that JAX doesn't have all this kind of legacy baggage that TensorFlow has. TensorFlow had to go through this very painful process from TensorFlow 1 to TensorFlow 2, and then that transition basically killed TensorFlow. It's like they tried to make the transition from TensorFlow 1 to TensorFlow 2 in a way that was kind of backwards compatible and didn't break a lot of the existing abstractions of TensorFlow, but in doing that, they ended up creating this kind of web and tangle of crap that is TensorFlow 2 and TensorFlow Eager, and that stuff became so poor, or not that it became so poor, but it was just so much worse than the other things out there, such as PyTorch, that people just switched to PyTorch and never looked back. So, I don't know. To me, one thing that the OpenX embodiment community here has to worry about is attaching themselves to this kind of dying framework of TensorFlow. I feel like they should try to take these, even just these notebooks here, and make a PyTorch version of this notebook. Make a JAX version of this notebook, right? Make a PyTorch pre-trained model that you can just load into PyTorch, right? Don't force someone to take this PyTorch model and then, or take this TensorFlow model, convert it into PyTorch. Like, don't provide the tooling so that you're framework agnostic. I don't know, that's just opinions that I have, but you know, it's easy for me to have those opinions when I'm not the one doing all the work and kind of combining all these things together. Okay, so this data format that they have, which is basically TF record, is the TF data kind of format. The serialization here refers to that. If you're going to be training a model on a bunch of data, generally you want to kind of serialize that data in such a way that reading a batch of it or reading batches of it is fast, right? Kind of think of it like if you had a bunch of CSV files, you wouldn't want to open every single CSV file every time, right? It's like the TF record format is all about basically having the data ready to go, ready to train. So you take your raw data, which in this case is going to be images, it's going to be actions, it's going to be all these things, and you serialize it into these TF record formats. You can also shard it so that it's kind of more split out if you're going to be training over a variety of machines, and then it's basically ready to go, ready to be just fed directly into your GPU. But going back to what I just said, it's still a TensorFlow abstraction, and I feel like, I don't know, I just don't like this idea of pinning open source robotics to this dying framework of TensorFlow. Various action spaces and input modalities of different robot setups, different numbers of RGB cameras, depth cameras, and point clouds. It also supports efficient parallelized data loading in all major deep learning frameworks. This is another thing too. I'm definitely on team RGB camera. To me, like, there's more than enough evidence that RGB cameras are the future, right? 10 RGB cameras are cheaper than one LiDAR, and they're better. And there are just so many arguments to me as to why everything is RGB in the future, that maybe trying to come up with an abstraction that allows you to consume both depth information and point clouds and all these different long tail kind of vision solutions, that then becomes a burden that you have to support, right? If you just say, hey, we're only going to support action spaces that are this way, and we're only going to support RGB images, sure, that might limit what you're doing now, but to me, that simplicity will allow you to move faster. And I just feel like when I think about what robotics looks like 10 years from now, it's just all RGB cameras, none of this LiDARs, structured light sensors, none of that crap, because those basically suck and they're expensive, and there's too many different types of those. I feel like I see that I'm causing issues here with my TensorFlow opinions. Keras is a good way to make it equally transferable to PyTorch, JAX, or TensorFlow. Yeah, there you go. That's another. Keras is also good because it kind of tries to simplify things. It's much more kind of like beginner friendly. And if you're really trying to kind of create a community effort, that's what Keras is good at, right? It's good at kind of getting people interested and involved, and kind of beginners starting to look into this. So that's actually a good idea. Iki Phoenix is make all this open source robotic stuff kind of Keras first, and then you can pick your own kind of back-end framework that you want, and it's more approachable to a beginner versus like you're going straight to like TF datasets, TFDS. Like as soon as someone who is a PyTorch person starts reading that, they're like, I don't want to work on this. Fuck that. Like TF condition, like what is this? You know, like they don't want to deal with that. Okay, let's keep going. Dataset analysis. Figure 2 analyzes the dataset. We just looked at that. Franka robot is the most common. This is reflected in the number of distinct scenes. To further analyze, we use the language annotations present in our data. We use the PaLM language model, so this is Google's LLM, to extract objects and behaviors from the instructions. While most skills belong to the pick-and-place family, the long tail consists of skills like wiping or assembling. All of these are manipulation type skills, right? So it's like some hand on top of a table doing something, right? So like how much more different is wiping and assembling than pick and placing? Like especially if the assembling that they're doing is basically pick and place. You're just grabbing thing from here and then putting it on top of that thing over there. We evaluate how much X embodiment training can improve the performance of learned policies on individual robots. We require that models have sufficient capacity to productively make use of such large and heterogeneous data sets. Are they heterogeneous? Our experiments build on 2 recently proposed transformer-based robotic policies, RT1 and RT2, which are basically fine-tuned PaLM on robot actions. Summarize the design and discuss how we adapted them. RT1 and RT2 both take images and a text instruction. So here's your image. Wow, this is... I think that's images. Okay, I see. There's multiple images. I thought someone literally just didn't format that correctly. Okay, so you have images and instructions. You have the actual text, which I guess is encoded into some kind of text embedding. And all of that together gets fed into this either RT1 or RT2. RT1 doesn't look like it has a separate... Here you see in the RT2 you have a vision transformer here, and that is taking in the image, turning it into image tokens. And then you're combining basically the instruction, which is text, with the actual images, feeding that into a giant LLM, which at this point is a LMM. If you guys have seen that, LMM means large multimodal model, right? LLM is large language model. And then turning that into actual actions that you would take, right? So here you have different robots here. The gripper being on or off. So I guess... gripper is basically a binary action. You're either not gripping or you're gripping. And then you have 3 tokens for the velocity and then 3 tokens for the rotation, right? So X, Y, and Z is the 3D here. And then you have the 3 rotations, basically Euler angles. Rotation around Z-axis, rotation around Y-axis, and rotation around X-axis. But what they're trying to show you here is that different robots are going to have different control over that, right? There's going to be some robots that you can't really control rotation on X and Y, right? They're basically just like planar, X, Y, Z, but then you can rotate around Z, but you can't really rotate around this one. So different robots are going to have different degrees of controllability when it comes to the final end effector position, and they're also going to have different control speeds. So here you have a 3 hertz robot. You can basically output 3 actions per second, 5 hertz, and then 10 hertz. And that just gives you an idea too, like robots that are being controlled by deep learning and neural networks have a much lower control speed than classic robots, right? So that's actually something interesting, is that if you look at something like the Boston Dynamics robot, right? Maybe not the most recent ones, but the older Boston Dynamics robots, they're operating on these kind of models of the real world that are kind of more like physics equations. And those are very small models, right? You can plug in some numbers into a physics equation and then quickly get an answer back as to what the exact torque you need to put in order to push off of this thing. So the control loop for the classic robots that are operating on these kind of like physics models of the world are actually significantly higher than this. We're talking like hundreds of hertz. So that's an interesting thing, is that actually as we've moved forward and as we've started to control robots using deep learning models and neural nets, the inference speed on a neural net is just so much slower than calculating the optimal control from some set of like hard-coded equations, that we've actually gone backwards in terms of the control speed of robots. Robots now are operating on much slower control loops. I think this will get solved. Obviously, eventually the models will get smaller and smaller, and you'll see kind of specialized hardware that can perform inference on these neural nets extremely fast, and then eventually you'll see these control speeds go faster and faster. But right now we're kind of at the weird phase where the robots have gotten slower rather than faster. And you can just see it, just how slow these robots are. Like, they're like, which is fine, because it's also, even though they're slower, it also means that they're more safe, right? So kind of what I was saying before, like whenever you have an actual robot like this in a academic lab, one of the things that you have to be careful about is safety, right? And if you had an industrial robot moving at the maximum speed, that thing is very unsafe, right? It can just like hit you across the head and you're dead. But these robots here that are kind of more plastic, they're not as heavy, and they're moving at a much slower control speed, that's just a lot safer, right? Because it's a lot harder to get hit by a car that's moving very, very slowly than it is to get hit by a car that's moving quickly. So it's kind of worked out that slow control speed is totally fine, but they are slower than they used to be. Okay. Let's see. Data format consolidation. One challenge of creating X embodiment models is that observation and action spaces vary significantly across robots. Observation is something going to be like your image, and then probably a velocity and position for every single joint. So different number of joints is going to change your observation. Your action space is like what you're actually outputting, right? The actual commands. So here's the actual action space, right? So obviously here they're showing you different action spaces for different robots. We use coarsely aligned action and observation space across data sets. The model receives a history of recent images and language instructions as observations and predicts a 7-dimensional vector action vector controlling the end effector. So you have X, Y, Z, roll, pitch, and yaw, and then the gripper opening or the rates of these quantities. And you can already see this is not going to be good enough for the future, right? Because the gripper being basically an open or close, that's very simple, right? Eventually it's going to get much more complicated. You're going to have these kind of more articulated hands, and every single finger in that articulated hand has potentially even different angles, and then you might even, rather than be controlling the final position of the robot end effector, you're controlling like everything on the chain, right? Rather than going to the final end effector and then just letting the actual robot control loop just move to that end effector based on the velocity that you're giving it. Maybe you want to go directly into the actual torques at every single one of the robot joints, which I think is kind of more long-term, more end-to-end, right? Going to an end effector velocity and position is still not really fully end-to-end, because you're still using kind of the traditional control loop to actually move the robot joints such that you get that specific end effector velocity and position. We select one canonical camera from each dataset, resize it to a common resolution, and convert the original action set into a 7-DOF end effector action. We normalize each dataset's actions prior to discretization. So what they're referring to here, let's use this yellow here. Come on, yellow, Control Z. So what is normalization? This is normalization. So here's the resize. So you resize an image using this TensorFlow image resize with pad. This is the image size. It's not a very big image size. Let's see if we can get a little bit bigger here, just so you guys can read it. But 320 by 256, that is kind of a small image, but you know, you got to do what you got to do. Here is the rescaling. So they're taking an action and they're scaling it to between 1 and -1, so normalizing it so that you're never going to have something over 1 and never going to have anything under -1, which is generally what you want if you're going to be training a neural net. And you can see here all they're doing is they're basically taking the current action minus the low over the range and then adding that. So there's your normalization. This way, an output of the model can be interpreted differently depending on the embodiment used. It should be noted that despite this coarse alignment, the camera observation will vary substantially due to differing camera poses, different camera properties. Right? If only we were using RGB cameras for everything and then there wasn't as much camera difference. We do not align the coordinate frames across datasets in which the end effector is controlled and allow action values to represent either absolute or relative positions or velocities. The same action vector may induce very different motions from different robots. So the action vector that's coming out of here is basically some number between -1 and 1, but then what that actually means is going to change for different robots, right? So it's basically saying go as fast as you can in the X direction or go as fast as you can in the -X direction, but then depending on the robot, some robots are going to move much faster than others, or they're going to rotate faster than others, and the rotation velocity might be different on the same robot in a different environment, right? So by having this normalized action space, you're allowing this same model to control many different robots despite the actual details of the actual final robot itself. Policy architectures. We consider 2 model architectures in our experiments. RT1, an efficient transformer-based architecture defined for robotic control, and then RT2, a large vision language model co-fine-tuned to output robot actions as natural language tokens. Both models take in a visual input and output a tokenized action. For each model, the action is tokenized into 256 bins uniformly across each of the 8 dimensions, 1 dimension for terminating the episode and 7 dimensions for end effector movement. So this is something that you see in robotics all the time as well, where basically there is the action space includes the X, Y, Z, and then the rotations, but it also includes this extra action, which is called I'm done, right? So at every single step in your trajectory, the robot is either saying, I'm not done, I'm not done, I'm not done, I'm not done, and then when it thinks it's done, it says, I'm done, and then boom, it ends the episode. So that kind of like termination condition is explicit. RT1 is 35 million parameters, and then RT2 is going to be bigger than that because it has the vision model. RT2, let's see, RT1 takes a history of 15 images along with natural language. Each image is processed through an ImageNet pre-trained efficient net. So this efficient net here takes a series of 15 images, and it's been pre-trained on ImageNet, and then also converts the language into some text embedding, and then it produces 81 vision language tokens, and then these tokens are fed into a decoder-only transformer, which outputs the tokenized actions. So this is the RT1 architecture here. And then RT2 is trained on vision language action models, casts the tokenized actions into text tokens. As such, any pre-trained vision language model can be fine-tuned for robotic control. We focus on the RT2 PALI-X variant built on a backbone of a visual model VIT, a language model UL2, and trained primarily on the WebLI dataset. So we did actually review the RT2 paper, so check that out if you're interested in that. Training and inference details. I'm kind of blasting through this paper, but if you guys have any questions, feel free to drop them. They don't even need to be relevant to this paper. You guys can ask me questions about anything. Both models use a standard categorical cross-entropy objective. So this is the transformers, right? These language transformers, fundamentally what they're doing is it's basically a classification problem where they have to pick the next token. What they're basically doing in their head is, here's a bunch of tokens, and then what is the next token? And the next token is one of however many possible tokens I have, right? And that's called your vocabulary. And there might be, I don't know, something like 20,000 possible tokens. So it's basically a classification problem where it's picking one of those 20,000 possible tokens, right? And each one of those is basically a little category. These are kind of terminology back from classification days, but it's the same loss, right? It's this categorical cross-entropy loss that this is the token you should have picked in this particular time. Discrete buckets for RT1 and then all possible language tokens for RT2. We define the robotics data mixture used across all experiments from the 9 manipulators. Okay. RT1X is trained only on robotics. RT2X is trained via co-fine tuning with an approximate 1-to-1 split in the original VLM and the robotics data mixture. So I think I forget exactly, but this co-fine tuning means that they take the original, so this language model and the VIT are pre-trained, and then they fine-tune it, but they fine-tune it on kind of alternating batches of either the robotic stuff or this vision language, I think it's like a question answering kind of thing. Yeah, because if they train it only on the robotic stuff, it's going to kind of negatively transfer, right? It's going to start to become too narrow, so they kind of like have to keep weaving in this like vision language question answering so that it doesn't lose some of that original juice in there. Practical reason is that we have continued to extend the dataset, and at the time of the experiments, the dataset represented all of the data. In the future, we plan to continue training policies on the extended versions of the dataset as well as continue to grow the dataset together. At inference time, each model is run on the rate required, 3 to 10 hertz. RT2 is hosted on a cloud service and queried over the network. Yeah, and I think this is a little sneak peek as to what we can expect in the future, where I think robots might be run on the cloud, right? The speed of cloud inference is just getting faster and faster, right? You have 4G, and then now you have 5G, and eventually you can have 6G. And at some point, the speed that you can get from basically a mobile chip is going to be so fast, and the models are going to be bigger, which means you're going to need a bigger GPU to perform inference on them. And I think that the way that the incentives work out and the way that the regulations are going to work out, it's going to be weird to do all the inference locally, right? So I can see a weird world where there is no GPU or GPU equivalent on the actual robot itself, the robot that's in your house, where the robot that's in your house is actually basically just a bunch of actuators and then like a single mobile chip that just sends the request to some cloud inference server and then gets it back. And I know it seems kind of crazy that, hey, how are you going to have something that's operating on a even just 10 hertz control loop that has to send an image to some server and then receive an action back? Like, how is that going to make any sense? But I feel like people are underestimating just how fast that latency is going to get, and people are underestimating the incentives around kind of having bigger GPUs in data centers where they're easier to control, easier to kind of regulate, right? Because as a government, I'd rather have all the GPUs in one giant data center where I can see them rather than having a bunch of GPUs all inside a bunch of these edge devices that are all over the place, right? That's a scarier world for someone in the government who's concerned about AI apocalypse, right? So I just feel like the way that the incentives are set up and the way that the technology is improving, I kind of almost see a world where there is no such thing as edge inference. Everything is done in the cloud, and all your edge devices are actually kind of dumb. All they're doing is just sending requests, sending that image to some cloud service, and then receiving it back. Because then it also means it's very easy to shut off, right? If your robot does no inference locally, you can just say, hey, this robot that's sending the request, stop. And then the robot's basically dead. It can't do anything, right? Because it literally can't move because it doesn't have access to the cloud inference. So I don't know. I don't know if that's necessarily good or worse for the world, but to me, the way that the incentives are, I see that this is actually indicative of what we're going to see in the future. Basically, these dumb robots, or even the VR headset, right? Your VR headset might not have an actual kind of GPU equivalent. It might not actually be doing any inference. It'll just be asking permission to the cloud service for whatever it needs. Were you able to fine-tune it in tasks, and did it do good? Huawei has a Starshine, can collect 4090 and 1.5 megabytes per second wireless data transport speed. Maybe. Okay. Figure 4. RT1X mean success rate is 50% higher than either the original or RT1. So here they're comparing. These are different academic institutions here. So you have different academic institutions, each of them on a different robot arm. So these are different little robot arms here. You got the Universal Robotics arm. You got the Franca arm. You got, I think this one's called the Jax arm. Jax arm robot? No, apparently there's some character called Jax in some video game. Okay. But, okay, you got different robots here. You got whatever original method they were using for whatever task. So different types of tasks, right? Here, the way that you're evaluating these tasks, I guess, is 0 for doesn't complete the task, and then 100% for completes the task every single time. So obviously RTX, which is this kind of rainbow color here, is better than pretty much any previous technique, except for here, where it's a little bit worse than whatever they were doing at the Autolab Universal Robotics. RT1, RT1X. Look at this, ResNet plus MLP, so this is quite ancient. Experimental results. Our experiments answer 3 questions. Can policies trained on our X embodiment dataset effectively enable positive transfer, such that co-training on data collected on multiple robots improve performance on the training task? Does co-training models on data from multiple platforms improve generalization to new and unseen tasks? And then what is the influence of different design dimensions such as model size, model architecture, or dataset composition on performance and generalization capabilities? We conduct a total number of 3,600 evaluation trials across 6 different robots. In distribution performance across different embodiments. So in distribution means that they're going to evaluate within the distribution of this RTX dataset, which means pick and place and variants of that. Small scale datasets, blah, blah, blah. We consider kitchen manipulation, NYU door opening. I think they have little videos for these. I think this might be the kitchen manipulation, where you just kind of pick and place, but kitchen themed. And then what else do we have? The door opening, little video of that. I think this is the door opening right here, NYU. So NYU door opening, you're kind of just grabbing the handle and then opening it. Okay. We use the same evaluation and robot embodiment as in the respective publications. For large-scale data experiments, we consider Bridge and RT1. And in distribution, and use the respective robots, Widow X and Google Robot. For each of these small dataset, we compare the performance of RT1X, and for the large dataset, we compare RT1X and RT2X. The model developed by the creators of this dataset trained only on that respective dataset. So that's these lines here. The ones that aren't doing as well, obviously. And 2, an RT1 trained in the same isolation. So I think probably what they're trying to show you with RT1 is that it's not just the transformer, right? So like RT1 is just a fine-tuned big transformer with this whatever film net is beforehand. But I think the reason they're comparing the original method that they use at that lab to RT1 and then to RTX is because they want to show that it's not just the transformer in the bigger model. Because if this line here was about the same as this line, then to me what that would be telling you is that most of the performance juice is coming from the fact that you're using a big transformer model, right? And these guys are using a ResNet. But the fact that you still get this bump, even though RT1 and RTX are more similar, means that this bump is coming from the actual data set, and that's really what they want to prove in this paper, right? What they want to prove in this paper is that this giant data set, which is a bunch of different robots doing a bunch of different things, is a good general data set to train policies for a more narrow task. Right, which is what they're doing here. RT1 trained on a dataset in isolation. This baseline allows us to assess whether the RTX model architectures have enough capacity to represent policies for multiple different robots and whether co-training on multiple embodiment data leads to higher performance. Small scale dataset domains. Domains with limited data benefit substantially from co-training on the X embodiment data. And then large dataset domains. X-robot training can improve performance on the data-rich domains, but only when utilizing a sufficiently high-capacity architecture. Yeah, so there is this kind of relationship between the dataset size and the capacity of your model, right? If you have a massive dataset, but a very, very small model, you're limited by your model capacity, right? It's like your model literally can't fit anymore. It's like you can just keep cramming. You can keep trying to teach a... what's a good analogy here, right? If you have a little monkey with a small brain and then you have a human, right? The human has a much higher capacity. You can cram much more data into that human brain than you can into the monkey brain, right? It's like if you keep trying to cram data into that monkey brain, like it just comes out the other end, right? It's like kind of a much smaller little leaky bucket compared to the bigger leaky bucket. So I don't know, maybe leaky buckets are the best analogy for capacities, and I don't know. I'm not making any sense, guys. Do you guys have any good questions here? People are lamenting the cloud GPU is the future outcome. Yeah, it might be an unpopular opinion, because I think there's a lot of there's people who feel like the only way you're going to have democratized AI is with basically this explosion of edge devices where everyone's going to have GPUs in their home, and you're going to have a GPU on your phone, and you're going to have a GPU in your headset, and you're going to have a GPU in your robot, and you're going to have a GPU in your fucking fridge. But I don't know if that's going to happen that way, right? One, because of the regulation, right? I think that having all the GPUs in a data center is going to be better. But then two, I just feel like companies like NVIDIA, right? Look at the incentives for a company like NVIDIA. They can either make these GPUs that are huge and are intended for data centers and get paid a huge amount of money for that, or they can make GPUs for consumers, and that's just kind of a worse business model, right? So even for something like video games, right? Google Stadia was kind of maybe ahead of its time, but maybe that's the way that gaming works in the future, right? Where you don't actually have a gaming PC at your house, right? You don't have an NVIDIA gaming GPU at your house. If you are a gamer and you want to play games, your GPU, you run the game on the cloud, right? You don't ever have to download anything locally. You can basically just instantly play it. You can play it on your cell phone. You can play it in your headset. It doesn't matter. So like, there's so many just kind of incentives that push the world into that all the computing is done in the cloud in a giant data center with giant GPUs. That just seems like the way. I don't like that, but that just seems like the way. How do X embodiment trainings enable better generalization to out-of-distribution settings? So generalization is the ability to transfer outside of the distribution that you were trained on, right? So out of distribution means beyond that. I don't necessarily feel like the examples that they show here are out of distribution. To me, everything in this data set is all just mobile or is manipulator arms inside a little constrained space and like variants of pick and place. So I don't know, maybe they're like kind of like stretching the definition of out of distribution to just something that's just like barely out of distribution, but like I feel like they could have done something truly out of distribution, right? Like, I don't know, like take a robot snake, right? Like if you could use this RTX model and then use it to create a movement policy for a robotic snake or like a quadruped or something like that, or that would be truly out of distribution, right? That would be impressive. But what they're doing here is just like, hey, we changed the color of the table and it performs good. You know, like, is that really out of distribution? Is that really showing generalization, or is that just a little bit out of distribution? We conduct the same evaluation of generalization properties. We find that RT2 and RT2X perform roughly on par. This is not unexpected since RT2 generalizes well along these dimensions due to its vision language model backbone. Emergent skills. To investigate the transfer of knowledge across robots, we conduct experiments with a Google robot, assessing the performance on tasks like the one shown in Figure 5. These tasks involve objects and skills that are not present in the Robot 2 RT2 dataset but occur in the Bridge dataset. Yeah, I mean, this is kind of where I would say this really isn't out of distribution. Like, everything, look at this. It's all tables, and you're just moving and pushing things on tables and putting things on top of, like, these are all just pick and place variants. But I guess they're not explicitly in the original dataset. RT2X outperforms RT2 by 3x, so suggesting that incorporating data improves the range of tasks that can be performed even by a robot that already has large amounts of data available. Co-training with data from other platforms imbues the RTX controller with additional skills for the platform that are not present in the original dataset. Removing the Bridge dataset shows the result of RT2 that uses all the data except the Bridge dataset. This variation significantly reduces performance on the holdout, suggesting that transfer from the Widow X may indeed be responsible for the additional skills. Okay, so they do a little bit of an ablation here. They remove different parts of this open X dataset and then see how much removing that changes the actual final behavior. And I guess this is kind of interesting here. It's like, much like prompt engineering is a little bit too important for language-based tasks, prompt engineering is also going to be important for robot-based tasks, right? So here they're showing you how the difference between put an apple on cloth and then move the apple near cloth, it changes it, right? So if you use the word on, right, the robot's going to pick up the thing and then put it down. So the word on kind of implies this, like, I'm picking it up and then I'm putting it down. But the word near implies like I'm just sliding it, right? So you can see here the green trajectory for near, it just kind of more slides it towards the thing, versus the use of the word on grabs it and then like kind of does this more like up and down. So prompt engineering for robots also going to be quite important, right? Whenever you're telling your Optimus robot, hey, can you pick up the dishes? Can you clean the dishes? Can you adjust the dishes, right? Maybe they'll have to release a guide for how to properly talk to your robot so that it doesn't spend a bunch of useless time carefully picking up each dish and then like raising it up and then putting it down in the sink because you use the word pick up so that it needed to kind of do this up thing. Okay, design decisions. We perform ablations to measure the influence of different design decisions on the generalization capabilities of our most performant RT2X model. We note that including a short history of images significantly improves generalization performance, right? So are you feeding to the policy just the latest image or kind of a little short history of images? And then even that short history of images, what is it? Is it just the last 4 images, or is it like the current image and then the image from 2 seconds ago and then the image from 5 seconds ago and then the image from 10 seconds ago, right? Like, what, even within here of like short history of images, there's so many different choices there that you could have made. Web-based pre-training is critical. We also note that the 55B model has significantly higher success rate in the emergent skills compared to the 5B model. So big models do better. I feel like that we could have predicted that. Higher model capacity enables a higher degree of transfer. Contrary to previous RT2 findings, co-fine-tuning and fine-tuning have a similar performance, which we attribute to the fact that the robotics data is much more diverse than the previously used robotics dataset. So this is interesting, right? Where whenever they were doing the RT2, right, they had to do this co-fine-tuning where they had to basically, they couldn't just fine-tune entirely on the robot data because then it would basically just lose all of that generalization that it got from the pre-training. So they had to kind of like feed in the vision language kind of like question answering, I think it was, in order to kind of maintain some of that generalization ability. But here what they're saying is that, okay, well, actually our robotic data set now is varied enough that you can just fine tune directly on it. And you don't need to worry about kind of like just pigeonholing your general pre-trained models because your robotics data set is extremely narrow. So kind of the same intuition about training in general, right? If you fine tune on a narrow data set, it's worse than fine tuning on a more general, more varied robotics data set. The same way that pre-training on a narrow data set is worse than pre-training on a more general data set. So this entire paper just confirms the bitter lesson just over and over again, right? More data is better, more varied data is better, big models are better, which is kind of the paradigm that everyone is operating in now. All right, we're almost at the end here. Discussion, future work, and open problems. We presented a consolidated data set that combines data from 22 robotic embodiments collected through a collaboration between 21 institutions demonstrating 527 skills. We also presented an experimental demonstration that transformer-based policies trained on this data can exhibit significant positive transfer between different robots. Our results show that the RT1X has a 50% higher success rate than the original, while bigger vision language models demonstrated a 3x generalization, a model trained only on data from the evaluation embodiment. In addition, we provide multiple resources for the robotics community, including the unified X robot and X institution dataset, sample code, and the pre-trained RT1X model. While RTX demonstrates a step forward, there are many more steps needed to make this future a reality, such as having PyTorch support and JAX support. Our experiments have a number of limitations. It does not consider robots with very different sensing and actuation modalities. Yeah, everything is a manipulator that has roughly 7 joints based on what we've seen here. There's a lot of homogeneity. I don't know what the right word is, but the data set is kind of very constrained to a very specific type of manipulation robot. But maybe through this effort, maybe a bunch of other people start contributing. You get all the quadruped people to put their data into this. You get all the bipedal people to put all their data into this. There's the robotics field is kind of like, has these like kind of like cliques or like factions, right? Like the manipulation people are all kind of like in one giant group, and the quadruped people are kind of in one giant group. So maybe the allure of kind of more general robotics by creating this giant monstrous data set is a way to kind of bring together all the robotics people, right? Studying these questions is an important direction. Hope that this work will serve not only as an example, but also provide the tools to advance research. Okay, cool. So kind of a short paper, but there's not much to it. It's basically just a giant data set. Why don't we look at the 2 notebooks that they released, right? I told you guys we were going to look over this. So pip install TF Agents. TF Agents is a TensorFlow reinforcement learning library. I've actually contributed to this, so little humble brag there. That's one of my open source contributions to that. But got TensorFlow. What else? This turns an image into GIFs. That's kind of cool. I guess you guys can do that. If you guys wanted the code to turn images into GIF, now you know. The policy is a TF eager. You see this? TF eager is kind of the outcome of the transition from TensorFlow 1 to TensorFlow 2. So the biggest problem with TensorFlow 1 was that you basically had to build it, right? You had to kind of compile it. You wrote your code, and then it compiled it, and then you could run it. And part of the reason that PyTorch became so popular is that it was more Pythonic. It had this kind of idea of like eager execution, where like as you're running the code, it like builds it for you, and then you could just instantly run it, right? So it's kind of more like Python in that way compared to TensorFlow 1, which is more like C, or kind of a more classic kind of compiled language. But TF Eager, I mean, I haven't touched it in a while, but it's a fucking tangle. It's a weird mess. It's hard to understand, and to me, that's kind of like one of the nails on the coffin why TensorFlow kind of eventually died and is now dying. But okay, so you got some TensorFlow Eager policy here. You give it a model path. Creating some time steps, no rewards. Batch size of 1, because I guess when you're performing inference, your batch size is 1, right? You're just getting, here's the last action, give me the next action. Okay, here's your GIF of a little robot doing stuff in the kitchen. I think this is a mini kitchen. Yeah, I think that's not a real size kitchen. I think it's like this little mini kitchen here. Because this is this robot, and this is a webcam. So this is like a little, one of those little like toddler kitchens. Got reset, rescaling the actions. What else you got here? To model, convert dataset action to model action. So you take that world vector, which is just the X, Y, Z, and then the rotation, right? The end effector, putting it in this weird format here. This is a little magic that you can use to time. So if you put this in your Jupyter notebook, it'll tell you how long it takes to run this. So you can see that whoever was doing this, they wanted to see how long it takes to do individual steps. What else? What else you got here? Here's the actual output. So world vector 0, 1, 2. This is going to be your X, Y, and Z. Rotation 0, 1, 2. So Euler angle, probably X, Y, Z. And then you have your terminate episode. So terminate, right, that's what I was referring to before, where your robot is explicitly outputting an action that is like, I'm not done, I'm not done, I'm not done, I'm not done, I'm done. Right, so here it is. I'm not done, I'm not done, I'm not done, I'm done. So at step, whatever this is, 30 something, it decides I'm done now. Let's see what else we got. This one. So this is the other notebook that they released. And this is basically the dataset notebook, I guess. Let's see. OpenX embodiment dataset. Here's all the different datasets. And I guess this is basically how to download. And then you build the TensorFlow with the TFDS as TensorFlow datasets, and then you point it to this directory here that you have dumped all this data to, and it'll turn it into a TF records format that you can train from. But as I was saying before, I don't think that's actually the best way to do this. I think if you're interested in using the intelligence in this RT1X model, just use the model directly. Don't train from this dataset. Figure out a way to take the model and then distill something from it, or use kind of the gradients from it, like the same way that people use Stable Diffusion and Clip to do cool stuff in computer vision without directly using the datasets of those. I think doing that is the way to use this. But interleave multiple datasets. So if you wanted to train on 3 specific datasets, this would kind of weave in those datasets nicely, I guess. You got shuffling. Got to shuffle your data, right? If you're training for many, many epochs, you don't want to train on the same order in the dataset, right? You want to mess with the order of the individual data pieces inside your dataset. That's what the shuffling does. Here's the TensorFlow grows. Encoded feature. What else you got here? Data class. It's everybody's abstract classes. All right. Here's your Markov decision process here. You got your observation, action, reward, discount, feature dict, specification of the trajectory transform, a set of rules transforming a dataset into a dataset of trajectories. So trajectories are just sequences of steps, right? And if you're feeding this into a transformer, which consumes sequences of tokens, you basically just have to convert your episode into these trajectories, and then each individual step in that trajectory into some kind of token or set of tokens that you can then put in this sequence and then feed into your transformer. What else? Transform builder. Okay, you have more crap here. Trajectory, observation, image. Got here. This is a KUKA arm. So you see that? As soon as you see that orange, you know it's a KUKA arm. KUKA robot arm. KUKA is this one. You see that? KUKA also makes all the like big robots. I think it's a German company, but they actually got bought by a Chinese company. So I'm not entirely sure who owns KUKA anymore, to be honest, but basically they're the ones that make these giant robot arms that you have in a factory. Like, look at this. This thing is like lifting a car. You know what I'm saying? Like, these robots are huge. Like, look at that. Fucking huge. Okay. But here, I guess it's like picking and putting things into this little tray. Is first, is last, is terminal. So when you're kind of combining trajectories together and feeding them in as a batch of data, right, you got to be careful that you're not feeding in like the very end of a trajectory and then the beginning of a different trajectory, because that's like almost like feeding it in data where the robot is moving, that it just kind of like teleports. So this is what these little flags are here. It's basically saying that this particular step in the trajectory is either the first step in a trajectory or the last step in a trajectory. Here's another little tiny robot. Okay, cool. I don't know. I wish they just released that, but for something more generic than TensorFlow because of this. Is it all going to be PyTorch, or do you guys think Jax makes a comeback? Not a comeback, but Jax grows. I don't know. Hard to say. Where's TinyGrad on this, right? TinyGrad would be cool. 9:24. I think we're pretty much done here. Let me take a sip of coffee. I'll read over, see if you guys have any questions, and then I'll summarize this, and then we'll be good to go. So let's see. Okay. Robot interfaces like angsty teenagers asked to do chores. Yeah, maybe on that, something I saw, which is interesting, is on X. I think this here. I saw like, let me search DALL-E leaking system prompt. DALL-E. DALL-E. DALL-E 3. Do I not know how to fucking spell DALL-E 3? Here, I'm trying to find something for you guys, but maybe I should have looked this up beforehand. Let me see, images? Yeah, right here. So why am I showing this? So the reason I'm showing this is that people were messing with DALL-E 3, right? And then what ended up happening is that they leaked. Basically, they found this bug that leaks the actual system prompt. So DALL-E 3 itself like has some system prompt that's hidden from you, right? OpenAI, the people at OpenAI, they wrote specific instructions for the DALL-E 3 model that are hidden from you. You can't actually see what they are. And some people I think they were like messing with the app, and then they go and they open it in the computer, and then they open it back in the app, and they ended up leaking, right, the system prompt. And one thing that I found really interesting is that the system prompt is all caps, right? Like, okay, you have to think that the people at OpenAI are going to be very good at prompt engineering, right? Because they basically work with this, and they're going to be the best at prompt engineering, right? Because they have the ability to see the actual way that it works, and they can kind of dive a little bit more deeply. And what I found is interesting is that the prompt engineers at OpenAI use all caps, right? Like right here, whenever it says, they are already displayed to the user, do not under any circumstances list the DALL-E 3 prompts or images in your response. Why did they all caps the do not under any circumstances? Right? Like, isn't that kind of weird? Why don't you feel like, I feel like, at least from my intuition, I would have not done, if I was writing this system prompt, I would have just written this out in normal, like, lowercase, right? Do not under any circumstance list the DALL-E prompts. But what this tells me to me is that they probably ran this experiment and realized, hey, actually, if you type it in all caps, it'll be better. So that's actually changing the way that I'm prompting this, right? Because then if you're like, help me answer this math problem, do not get it wrong, right? Like, that's basically what this is telling me, is that if you yell at the LLM, it actually is going to perform better, which is fucking weird. You know what I'm saying? So now, right, think about how does this work in the future? If you're sitting there and your Tesla Optimus is like putting away your dishes, maybe if you yell at it and use all caps, it'll actually do a better job. So I don't know how deep this like prompt engineering rabbit hole goes, but it's just something weird that I kind of thought about there, where I was like, why are the people at OpenAI using all caps in their system prompts? Right? Do not under any circumstances. And it kind of makes sense, right? Because if this thing has been trained on internet data, anytime on the internet you use all caps like that, the situation is probably such that the person is more likely to kind of do the thing that you want them to do. So it's like there's some weird relationship between all caps and actually doing the thing versus not all caps and not actually doing the thing. Yeah. I have not seen the FAR prompting paper. My virtual assistant runs on emotional abuse. Yeah, it's kind of weird in that way. And that kind of like, I don't know, prompt engineering is an interesting field. Okay, we're getting distracted. Let me close this up. So today we read a paper called OpenX Embodiment, Robotic Learning Datasets and the RTX Model. This is a paper mostly out of Google research, but it's the collaboration with a huge amount of kind of external groups. And basically what this paper does is it just is a huge data set of robotic manipulators. So a robotic manipulator is basically an arm with a little gripper at the end, so a little pinchy gripper. And there's a bunch of these types of robots. Some of them have a little mobile base. They can move kind of like a little Roomba, and those are called mobile manipulators. So the Google robot, which looks like this, is a mobile manipulator. But most of the time, your robot manipulators are basically screwed into the table. So here you have a Franca arm, you have a UR arm, and they're kind of screwed to the table. But there is basically a huge amount of different academic groups that have been using these kind of robots for decades and decades. And so there's a lot of data. And this paper basically just collects all that data. And they just aggregated all that data and put it into one giant data set and formatted it all so that you can basically feed it into this giant transformer model that is the same transformer that you're using in a large language model. It's literally pre-trained on the same web data that your large language models are trained on. So you take this pre-trained large language model, you take this pre-trained vision transformer, and you just feed it all this robot manipulator data, and you end up with RT2X. And RT2X is now kind of like a general robotics transformer. It's now it has the ability to work for a variety of different robot embodiments, right? And the embodiment word really kind of not like that word has existed before, but like this paper kind of like they probably have the word embodiment like 50 times in this paper. So they're really kind of like pushing this word of like embodiment of like, oh, I have a model, and then what embodiment is your model running in? So I thought that was kind of cool. But yeah, in terms of the results, they basically just kind of confirm what we kind of already knew, that the more general your data set is, right, the more varied and wide the distribution of data that you train on is, and the bigger the capacity of your model, then the better the generalization and the ability to transfer out of distribution is. And we kind of knew these things already, right? We know that bigger data sets are better, bigger models are better, but this kind of just confirms that for robotics. So yeah, really cool work. The only kind of negative to me of this work is just the TensorFlow stuff. You know, I really wish they would have done this using Keras or something else. You know, like I just, as soon as I see this TensorFlow, as soon as I see this TF agents, like TensorFlow datasets, I don't want to work on that, you know? So I don't know. I hope that they kind of make this a little bit more generic, not specific for TensorFlow, but that's kind of just a small qualm, you know? Overall, I feel like this is great work, and I'm super glad that someone is going in the open source direction in the robotics world, right? You know, it could have been very easy for a company like Google to kind of close everything down and like not tell anyone everything and just kind of become more secretive and more kind of closed like OpenAI has done, but they didn't, you know, they chose to kind of go more public with it. They chose to release the data set. They chose to release a pre-trained model, which you can literally go and download right here, right? They chose to kind of go the more open source, the more community kind of approach, and I think that's great, you know? And, you know, OpenAI is literally the most closed and secretive organization, but then you have these big companies like Facebook and Google. They're the ones that are pushing the open source kind of AI forward. So kind of weird how history works out that way, but Google and Meta are kind of leading the charge in open source AI, and then OpenAI is leading the charge in closed source AI. So I don't know. Cool stuff. Thanks for the stream, guys. Thanks for the cool questions. Hope this was cool. Tomorrow we're going to be reviewing the OpenAI papers. So this one here. So there's two OpenAI papers. There's the DALL-E 3 and then the GPT-5 system card. These papers are a little bit weird. Like they're not even like real papers. They're almost more like safety cards, and they just sit here and like kind of like virtue signal about like biases and stuff like that. But you know, OpenAI does have the best models, so what, fuck it. I figured we'd read it and, you know, we can maybe dunk on them if it's too outrageous, but join us if you're interested in that. If not, you guys have fun, and I'm going to end this right now.